let's consider what we'll call downhill Hal. Winter Olympics will get here eventually, and Hal and Al are considering going out for the two-man luge. So they want to practice. So the track is set at an angle, just like we have here and as we've done before. And we're going to take Hal and start him up high, let him go down low, and see what happens. And you remember what happens. As soon as we let go, it accelerates. It accelerates due to gravity. The acceleration is reduced by the angle of the track. So we know what will happen is here, I release Hal from rest, no velocity. As we get here, gains some velocity. As it gets to the bottom, since it's accelerating, gains even more velocity. So what we have is that velocity increases. Now let's think about this in terms of energy. Well, what happens in terms of energy? The kinetic energy increases. Well, if the kinetic energy increases, the question is who or what is doing the work? That's what we have to figure out. The last time we said work is Fd, where F is the force that's pushing it through some distance. Okay, so all we have to do now, though, then, is figure out what is that force. Do a free body diagram. Okay, so we've done a free body diagram in this situation before. If you have Hal here, mg, of course, pulls down, and there's a normal force pushing perpendicular to the direction of the track. So if the track is roughly like that, the normal force is kind of out here like this. And if you really want to know exactly what's going to happen, then you do the vector sum of these two. Their components along the track cancel, that's why it doesn't fall into the track, and they have a component down the track, and that's what accelerates the ball based on the value of that angle. So that we all did before. But now we want to figure out how much work is being done by each of these forces. So before we go off and write it, we have to remember that the directions of the force and the displacement d matter. Why? Because they are vectors. You don't really just multiply mg times the distance d and n times the distance d. So if we say d is here from the top to the bottom, we have to think a little more carefully. It gets into ways to multiply vectors, but for now we're just going to give you the formula. We're not going to worry about, it's technically the dot product, but let's just write it this way. The work is the force that does the work times d times the cosine of the angle in between them. And of course we mean the angle in between the two vectors. Or it's also sometimes written like this, the force parallel component times d, where that means the component of the force along the direction of d. And if you do a lot of vectors, you'll know those are just the dot products. It's f dot d. But let's just mathematically stick with this. So these are the magnitudes. And this is the angle between. Up there. Oh, no, theta is the angle between, not cosine. Okay, so now we can look at them and figure out which one, how much work do they do. Let's look at the normal force. Let's see, for the normal force, the direction is always perpendicular to the surface, but the motion is always along the surface, right? So that's by definition, that's what the normal force is. It always points normal to the surface, so it's always going to be, the work is always going to be the normal force times the distance times the cosine, and that angle is always 90 by definition. If you move along the surface, your d is always along the surface. If your normal force is normal, then the force is always normal, and 90 degrees, the cosine of that is 0. The dot product of two vectors perpendicular is 0. So the work by the normal force is 0. Pretty much by definition. A normal force can't do work of something on something sliding along it, just because it's pushing the wrong way. That's what's keeping it up. So let's look at gravity. Gravity work would be the force of gravity, mg, which is down, times the displacement d, times the cosine of the angle between them. So then you look at these vectors and you say, okay, this is down and d is this way. So really d, like I said, displacement really is a vector, and mg is down. It's actually this angle of the triangle. It's actually that theta. If you write it as a cosine, it's that cosine theta. Right? Usually when we set this problem up, we call this theta. But actually for this problem, this is theta. Or you could switch from cosine to sine. That would be confusing. So let's just keep calling it cosine. So this is where the work is done. The work that gave it kinetic energy was done by gravity. And just like the acceleration is slowed down by going at an angle, how quickly you give it work is also slowed down by going at an angle. So gravity can do work on an object that changes its kinetic energy.